Morning, everybody. Happy Monday. Today we're discussing Stewart section 3.7, L'Hôpital's rule. Before we start that, I want to remind you of something. When we find a derivative of a quotient, it's not equal to the quotient of the derivatives. So you don't find the derivative of a quotient that way. You use the quotient rule. So this is a reminder about derivatives of quotients. So the quotient rule says the derivative of the top divided by the bottom is this crazy thing. So that's, yeah, Marceline?
The top of the second half of the equation shouldn't be prime.
All right, yeah, good. Now, however, there are certain situations where you do so there's certain situations. So this is not about these situations are situations that are not about derivative of a quotient. Where top prime over bottom prime is used. So again, it's not going to be the derivative of a quotient because I've already said very clearly, the derivative of a quotient you don't do by doing this. So a situation where you're going to be doing a calculation like this is something else. And so that brings us to section 3.7, L'Hôpital's rule. Now it's spelled L'Hospital's rule. So I'm going to say C derivative rules or limit rules on recitation 9 web page. So let's go look at that. So here we are looking at the web page for recitation 9. There's that huge list of derivative formulas, and then which you get to by clicking this button, and it reveals them. And then there's some stuff about L'Hôpital's rule. And notice that L'Hôpital's rule is not a derivative rule. It's a rule for finding limits, indeterminate limits involving quotients. So let's see what this says here. Click to reveal this. So first of all, a reminder of what we mean by a limit that's in indeterminate form. So here's a limit of a quotient. We say that it's in indeterminate form 0, 0 if the separate limit of the top is 0 and the limit of the bottom is 0. And then there's another indeterminate form, infinity over infinity. We say that the limit is in indeterminate form, infinity over infinity, if the limit of the top is either plus or minus infinity, and also the limit of the bottom is either plus or minus infinity. Okay, so L'Hopital's rule is can sometimes be used to find, remember, a limit that's in indeterminate form means you can't determine right away what the value of the limit is. You've got to do some more work. So in certain cases, you can use what's called L'Hopital's rule. So what are those certain cases? So it's a big if. Now in the book, this is all presented with F and G notation. I like using top and bottom notation because, well, they help remind you what role these functions are playing in the problem. So if you have a function called top of x and a function called bottom of x, and they satisfy all these conditions, first of all, the limit's got to be in indeterminate form. And then the top and bottom functions need to be differentiable near x equals a. And furthermore, bottom prime at a has to not be 0. If all that stuff is true, then you can, this equation is true. This limit, this indeterminate form limit, is equal to, so the limit of the quotient is equal to the limit of the quotient of the derivatives. So look, there's a situation where we're doing top prime over bottom prime. But look what's on the left side. What's on the left side of this equation is not a derivative symbol. It's a limit. So remember, I'm always nagging you about making sure that you show the left side of your equation, something that's valid that says what you're computing. When you're doing this, your left side should not be a derivative. Because again, no derivative has a right side that looks like that. So when you do one of these problems, you're going to be computing something like this. The left side, the way this all begins, is you've been tasked with the job of finding some limit. All right, now this equation is true whether the limit on the right exists as a real number or as infinity or negative infinity. That's one thing. And then also that we have the usual kinds of generalizations of the limit notation. So in this original equation, I'm thinking that x is approaching some number, a. And the generalizations are the usual one. We could have one-sided limits. So x approaching a from the right, or maybe x approaching a from the left. And we can also have a generalization of x going to infinity, or x going to minus infinity. All right, so see if I can leave that up for a little while. So this is meeting part 1. It should have said. So meeting part 1. I should have written up here. So introduction and basic examples. So we're still in that part of the meeting. So here's our first example. So consider this limit. the limit as x approaches 2 of x squared plus 3x minus 10 divided by x minus 2. So observe that that's in indeterminate form, 0 over 0. Now, we've had limits like this back in section 1.4. So I'm going to say, question A, find the limit using section 1.4 techniques. So let's see, here we go. The limit as x approaches 2 of x squared plus 3x minus 10 over x minus 2. Well, I'm going to factor this, start off. Limit as x approaches 2. This factors as x plus 5, x minus 2 over x minus 2. And then it's been a while since I got to write this. Since x is approaching 2, we know that x is not equal to 2, so x minus 2 is not equal to 0. So we can cancel. Now we need to have that limit notation in order to be able to say all that stuff. And furthermore, this is the most important step, so I show the before and after. Notice this is no longer indeterminate. All those scrunched together letters say that it's no longer indeterminate. So question B is find the same limit, but this time using L'Hopital's rule. All right, so I'm going to write down the limit on the left side. Limit as x approaches 2, and I'm going to go back to using the standard form. So there's my original limit, which is 0 over 0 indeterminate. Now I'm going to use L'Hopital's rule. So notice that with L'Hopital's rule, the limit symbol stays. So I have the limit of this quotient is the limit of the quotient of the derivatives. Now let's just get to work. The derivative of the top, so I still have to have my limit notation. The top prime is 2x minus plus 3, and the bottom prime is just the number 1. Notice that that's no longer indeterminate. And so I can just substitute in my numbers, 2 times 2 plus 3 over 1, so I get the number 7. Same exact answer. Okay, but big deal. Look, I used just as much chalk in method B as I did in method A. So why would I bother with method B? Why would I bother with L'Hopital's rule? Well, here we go. Let's do another example. Again, these are basic examples. Notice that limit is indeterminate form. Because the limit of the numerator is 0, the limit of the denominator is 0. Now, anybody seen this limit before? So I see some people nodding their heads. So what's the value of this limit? Say it again? No. Yeah. We saw that this limit, as x approaches 0, of sine x over x equals, well, there's some work here. We got the answer 1. But what was this work? It wasn't this simple. This involved, canceling some terms and making the form not indeterminate. This involved a very beautiful, well, I get to use my pumpkin spice chalk. Now, anytime a mathematician says something is beautiful, it means it's hard. Beautiful but clever. So AKA hard proof involving, well, geometry and the squeeze theorem. Very different style of proof than, we did a lot of those, proofs involving canceling. We didn't do this. I didn't do it. I'm always kind of afraid of it because I'm sure that I'm going to screw it up. So I urged you to go read the book because it's one of the really cool things about this book. One of my colleagues and I love this book in particular, well, because of the book's proof of this is one of the reasons that I love this book, and other people as well. So let's try to produce this result using L'Hopital. All right, so the limit as x approaches a of sine x over x is going to be, using L'Hopital, the limit as x, this is say x approaches 0, of sine x prime divided by x prime. But sine x is just cos x, and x prime is just the number 1. Notice this is indeterminate. This is not indeterminate. So I get to just plug in the number. I get the number 1. So it's a one-line proof. Not nearly as pretty as the book's proof. But this is one that you can actually do. Okay, example 3. Consider this limit. The limit as x approaches 0 of e to the x plus e to the minus x minus 2x on top and x minus sine x on bottom. Now this is indeterminate form, 0 over 0. But we don't have any techniques from section 1.4 that will help us solve this. So, again, this technique from section 1.4 that the book did was stuff that is at your level. I mean, it's geometry that you know, but you've forgotten. And the squeeze theorem, which you learned in section 1.4, but didn't use enough to get really good at. But it is technically stuff from section 1.4. But in this form, no techniques from section 1.4 can help us. So let's find the limit using L'Hopital's rule. So on the left side, we have the limit. So the limit of that quotient, e to the x plus e to the minus x minus 2x, divided by the quantity x minus sine x. So by L'Hopital, this is going to be the limit again. Now I'm going to just take the derivative term-wise. The derivative of e to the x is e to the x. Can somebody tell me what's the derivative of e to the minus x? Well, the outer function is e to the parentheses. So I take the derivative of the outer function. I put the original inner function inside, so minus x. And then I multiply by the inner prime. What's my inner prime? The derivative of minus x is minus 1. So this is a chain rule result right there. The derivative of e to the minus x is minus e to the minus x. Okay, and then we've got the derivative of minus 2x, which is going to be the number minus 2. And then on the denominator, we're going to have 1 minus cos x. So I'm going to clean up. The limit as x approaches 0 of e to the x minus e to the minus x minus 2 oops, this is supposed to be a minus sign. E to the x minus e to the minus x. E to the x minus e to the minus x. E to the x minus e to the minus x. So here, this becomes e to the x plus e to the minus x minus 2. And on the bottom, 1 minus cos x. So at the very beginning, if I had gone a little slower and verified things, we would have seen that this is indeterminate. Zero over 0. And look, when I plug in 0, I get e to the 0, that's 1. E to the 0, that's 1. So I get 1 plus 1 minus 2. I get 0 on top. In the bottom, I get 1 minus cos 0. Well, cos 0 is the number 1, so I get 0 on the bottom again. Dang it, it's still indeterminate. So we use L'Hopital again. So I still have the limit in front. And the numerator, the derivative of e to the x is e to the x. The derivative of e to the minus x is minus e to the minus x. The derivative of the number negative 2 is 0. And the bottom derivative of 1 is 0. The derivative of minus cos x is sine x. Now let's see what happens when I try plugging in 0 into this. I get e to the 0 is 1, e to the minus 0 is 1. Dang it, I get a 0 on top. And sine of 0 on the bottom, that's a 0 as well. Double dang it. So it's still indeterminate. So I'm going to just go over to here. We got to use L'Hopital again. So the derivative of the numerator is the derivative of e to the x is e to the x. The derivative of e to the minus x is minus e to the minus x, but I've got a minus sign in front already, so I end up with plus e to the minus x. And in the denominator, the derivative of sine of x is cos x. Now notice, this is not indeterminate. Very cool. If you plug in x equals 0, you don't get 0 over 0. Oops, I got to have my limit in front because grader dude is really grumpy about notation. Okay, so no longer indeterminate. So I can just substitute in my value. So I get 1 plus 1 over 1. So I get the number 2. That's not a result that you could have foreseen. Looking at this, you have no idea that this is going to turn out. And again, nothing from chapter 2, or from section 1.4 would have helped you. All right, so like as I said earlier, that was meeting part 1. I just introduced the rule, and I do some basic examples, no funny stuff. But this third example should make it clear, well actually the second and third examples that make it clear that this is a powerful tool, a useful tool. Meeting part 2. Indeterminate limits, so these headings, I like a long heading. So indeterminate limits involving products. turned into indeterminate limits involving quotients. So we're up to example 4. The limit as x goes to infinity of x to the 4th times e to the minus x. Now, this is a form infinity times 0. That's because the limit as x goes to infinity of x to the 4th, well, that's clearly infinity. That's a graph that's going up on both sides. And the limit as x goes to infinity of e to the minus x is 0. Remember why. We have a graph that looks like this. Y equals e to the minus x is a graph that's coming down. And so we're looking at this part of the graph. X is getting more and more positive without bound. The y value is getting closer and closer to 0. So the limit of that term is 0. So this is indeterminate form infinity times 0. We can't say right off the bat what that's going to be. So we're going to use a rule of exponents to say that this is the limit of x to the 4th over e to the x. So now we've got an indeterminate form that's a quotient. And it's an indeterminate form infinity over infinity. The limit as x goes to infinity of e to the x is infinity. So this graph goes up on the right, and so the limit as x goes to infinity of e to the x is infinity. Okay, so since we have a quotient, then we can use L'Hopital. So I'm going to have this equal to the limit of the quotient of the derivatives. So the limit in the numerator is 4x cubed. The limit in the denominator, oh goody, that's just still e to the x. But dang it, that's still indeterminate. Okay, well, let's go on over here. So we're going to use L'Hopital again. So we have to copy the limit down every dang time. The limit as x goes to infinity. Take the derivative of the numerator, and I get 12x squared. Take the derivative of the denominator, and I still get e to the x. But that's still infinity over infinity. Okay. So let's use L'Hopital again. So I'm going to get the limit expression. In the numerator, I'm going to get 24x and the denominator are going to get e to the x, still indeterminate. So let's see, we've used L'Hopital once, twice, 3, let's use it a 4th time. Got to always copy down the limit expression. That's not indeterminate. So I get out my special pumpkin spice chalk. I observe that x is getting huge and positive. So as my friend Andrea from Brooklyn would say, it's getting huge. So e to the x is really huge and positive. So 24 over to e to the x is going to be very close to 0. So all of this thinking allows us to say that the limit is 0. It's important that this quotient is never 0 because it doesn't have a 0 in the numerator. But the value of the quotient, it's getting closer and closer to 0. So this part of the limit of x to the 4th over e to the x, this is a very common kind of limit where you notice both those graphs go up on the right. X to the 4th goes up really fast. And, but this tells us that basically the e to the x graph eventually goes up faster. So this is a limit that compares the growth of the functions x to the 4th and e to the x. And the conclusion is e to the x grows faster than x to the 4th eventually. Grows faster eventually. It might not grow faster right away, but it does eventually. Now, more generally, e to the x grows faster than any polynomial. That's huge, or as Andrea would say, huge. So, consider the polynomial function x to the 1/millionth power. That function grows really crazy fast. Initially, it grows faster than e to the x, but eventually e to the x will grow faster than that as well. So this kind of thing is big. How many of you are studying computer science? Anybody? Or minoring? So in computer science, one of the things you're concerned about is when your data set grows, how much longer does it take your program to crunch that data? A lot of programs that you write, if you write a simple-minded program, it might turn out that if n is the number of data points, then the number of steps your program takes might be like e to the n. Well, that's crazy. Something that might work for 10 data points, e to the 10th, I can do that. won't work so well for 1,000 data points. E to the 1,000 is a gigantic number that you won't be able to wait. That's not a go down the hall and get your coffee while your computer crunches the numbers problem. You know, E to the 1,000 steps is going to take more time than you can do. On the other hand, if your competitor has a program that can solve the problem in a polynomial number of steps, the polynomial that depends on n, well, that's way better. Like, for instance, you know, suppose it's polynomial growth with a power of 3. Well, 10 cubed is 1,000. 100 cubed is whatever that is, 110,000. So it's a million, right? So you know you can pay for you can go have a cup of coffee. You won't even have time to get a cup of coffee if your computer is doing 1,000,000 steps. It'll be done before I finish this sentence. So deciding how fast functions grow is an important topic, especially in computer science. So this is a first example of a problem of that kind. It wasn't presented that way. We had an indeterminate product. We turned it into an indeterminate quotient, but that indeterminate quotient is a famous kind. Okay, meeting part 3. Indeterminate limits involving So go back to my wonderful long title. Remember what we did? We turned our indeterminate limit involving a product into one involving a quotient because L'Hopital's rule needs a quotient. L'Hopital's rule only applies to indeterminate forms involving the limit of a quotient. So that's why we needed to do that. Okay, so meeting part 3 is indeterminate limits involving expressions with exponents. So before we do an example, I want to review, first of all, cancellation equations. Those are these equations that a lot of you might remember from high school. ln of e to the x equals, altogether now, 1, 2, 3, what? X. All right, and then e to the ln of x equals, on the count of 3, 1, 2, 3, x. All right, everybody remembers those. And then there is a new fact about limits using the fact that e to the x is a continuous function and ln of x is also continuous. Now, I'm not going to get into the details of how that implies what I'm going to say, but the fact is this. If I have a limit of e raised to some f of x, I can move that limit. This is x approaching a. I can move that limit inside. So can move the limit inside the exponential. And there's another thing like this for ln of x. So if I have the limit as x approaches a of ln, and I'm going to say g of x, I can do the same thing. I can move the limit inside and get ln of the limit of g of x. So this is just an old friend. It's always good to revisit. This is a big deal. That there are a lot of limits. Well, we're going to do one. So this is example 5. Remember, I promised you that this was going to be examples involving indeterminate limits of expressions involving exponents. So here we go. The bad news is this is hard. The good news is this is the last thing we'll do today. Okay, the limit as x approaches 0 from the right of 1 plus or 1 minus 5x raised to the 1 over x power. Now notice when x is getting closer and closer to 0, the base is getting closer and closer to the number 1. But when x is getting closer and closer to 0, 1 over x is getting more and more positive because x is a positive number. So this is indeterminate form. One to the infinity. That is, you know that 1 to any power is just 1. On the other hand, any positive number raised to a higher and higher power blows up and becomes infinite. So we had this kind of thing before when I was introducing the number e. We don't know what this limit's going to turn out to be. So here we do a trick using the cancellation property or a cancellation equation. So I'm going to write this. E raised to the ln of that mess. Isn't that crazy? You know, e to the ln of this junk is just this junk. So again, this is a trick. If you're on a desert island and you have to come up with this, you're going to be stuck on the island because you would never think of this. I would never think of this. This was not my idea. It's above my pay grade. Now, we're going to use a rule of of logarithms. That says that a to the b, ln of a to the b is b ln of a. That's okay. B ln of a. So I'm going to bring this. So I've got my limit as x approaches 0 from the right of e raised to the 1 over x ln of 1 minus 5x. And that's equal to e, I'm going to clean this up. ln of 1 minus 5x, that's in the numerator. In the denominator, I just got x. So I just clean up. So this is the limit as x approaches 0. Now look, I've got something of the form limit of e to some function. Limit of e to some function. I can bring my limit inside. So the e raised to the limit as x approaches 0 of ln of 1 minus 5x over x. But this limit is let's see, 1 minus 5x is getting closer and closer to the number 1. So ln of 1 would be the number 0. In the denominator, x is getting closer and closer to the 0. So this is 0 over 0 form. So I'm going to use L'Hopital's rule. So I have e, and I have in the parentheses, I have limit as x approaches 0 from above. The derivative of ln of this is 1 over 1 minus 5x times minus 5. And the derivative of the thing on the bottom is the number 1. So let me put the y. This is because the derivative of ln of 1 minus 5x equals, let's see, the inner function is minus 5x. So my inner prime is minus 5. My outer function is empty. It's ln of parentheses. And so my outer prime is 1 over parentheses. So when I take the derivative of that thing in the numerator, what I get is 1 over parentheses with 1 minus 5x times minus 5. So that's where I got that. That's the limit. That's the derivative of the numerator. And the derivative of the denominator is x. So let's clean this up. The limit as, I have e raised to the limit as x approaches 0 from above of minus 5 over 1 minus 5x. That's not indeterminate. I applied L'Hopital's rule to that limit on the inside. Oops. I have 1 minute. So this limit is e to the minus 5 over 1 minus 5 times 0. So that's e to the minus 5. So that's 1 over e to the 5. That is a crazy hard problem. And notice all the steps we used. We used the trick, the cancellation equation trick. We used rule of logarithms. We used the trick about bringing the limit inside. We used L'Hopital. And then that was it, though. All right, thanks, everybody. So you'll see Kingsley tomorrow in recitation.